All right, this is Unit 5.1. Now, we've already gone over this slide in class, but I'm going to go over it one more time just to make sure we're all on the same page. Convex shapes are shapes that have all the vertices pointing out. Okay, pointing out of the shape. So all of my corners are going out. There's none of the corners that are going in. Whereas if, say, I had this arrowhead, this would be a concave shape because there's two vertices that are going inside of the figure, towards the center. I'll use that wording, so towards the center. Okay, so convex, concave. Regular, as we've already talked about, means congruent sides and congruent angles. Everything is congruent. Whereas non-regular, it could either mean that a side is not congruent to the rest, or an angle is not congruent to the rest, or that nothing is congruent at all. Okay. Then down here we have our angle measure equations. To find the sum of the interior angles, you would use this equation. And then if you were looking for one regular internal angle, you would take that equation, so n minus 2 times 180, and divide the whole thing by n, the number of sides. So the sum of the interior angles divided by the number of sides. And then for exterior angles, the sum of all the exterior angles is always 360 for all shapes. And the same thing would happen to get one regular external angle. You would just take 360 and divide it by n. Now let's move on to the rest of the PowerPoint. Properties of parallelograms. So polygons are multi-sided figures. They have to have straight lines. They have to be a closed shape. But parallelograms are a special polygon. Okay, they're actually a special quadrilateral in which both pairs of opposite sides are parallel. This is your definition. And actually, in this PowerPoint, we're going to use the definition at least once. So it's very good to know this definition. So to annotate my picture down here, what this means is that the opposite sides, okay, are parallel to each other. Which makes sense because you have even parallel in the name. Now when we're naming parallelograms, we're going to draw the shape and then just go around the figure. So either A, B, C, D, or I could do parallelogram A, D, C, B. Those are both options starting at A, and one is going this way, the other is going this way. I'll do this one in red. What you can't do, this is a wrong name, is you can't say A, B, D, C. Okay, that doesn't go around the shape in either direction. That cuts across, and you can't do that. Okay, so our first proof for parallelograms, let's just get some more information about these shapes, because there's actually a lot of information that we can prove since we know that both sides are parallel. So our given is that the quadrilateral is a parallelogram. You know that because of the shape. And we're trying to prove that opposite sides are congruent. So let's annotate this first. I know that my opposite sides are parallel. And that's going to be the definition of parallelograms. And then because I have parallel lines, I also have parallel line angle relations. That was a sentence. So I know that 3 is congruent to 4 and 1 is congruent to 2 because of the alternate interior angle theorem. Oops. Okay. Like I told you in that unit, those things don't go away. Okay, now as I look at this picture for other information, I notice that first off I have two different triangles. And it would be really helpful for my proof as I'm trying to prove, pieces of this figure congruent. It would be really helpful if those pieces were in congruent triangles, because then due to CPCTC, I could say those pieces were congruent. Okay, so that's the direction I'm going to go. I'm going to look at my picture and see if I can prove these two triangles congruent. Well, already I have two pairs of congruent angles, and then that side in the middle is congruent to itself. So yes, I can prove those two triangles congruent, and it'll be because of the angle side angle postulate. Then, as I said, we could use CPCTC to prove the sides are congruent to each other. All right, that's our logic. Let's go ahead and write out our proof. So I'm given that I have a parallelogram, PQRS, and this is given. And then off of that, I know that PQ is parallel to SR, and that PS is parallel to QR. And this is the definition of parallelograms. And literally all I'm doing is going down my notes over here, which means then that angle 3 is congruent to angle 4, and angle 1 is congruent to angle 2 because of the alternate interior angle theorem. And then I can say that PR is congruent to PR. It's congruent to itself because of the reflexive property. And then I can say that triangle PSR is congruent to triangle RQP. Make sure your angles match up due to the ASA postulate. And then finally I can go to my proof and say that PQ is congruent to RS and that QR is congruent to SP because of CPCTC. Couple things looking back over this proof. So make sure all of your notation, oops, forgot one. Make sure all of your notation is correct. Make sure that when you are naming your triangle, the letters all match up. And that when you're looking over your picture, you try to find all the available information. Annotate all the available information, and that can help you piece things together. Okay, because now we know a lot. And as we go into parallelograms, all of that stuff builds. You've got triangles information, you've got parallel line information, you've got angles, you've got segments, you've got all these definition and midpoint theorems, and all these other theorems and angles. We've learned a lot. So all of that is coming together now in these proofs. So if you've been maintaining your flashcards, excellent job for you. Go back through and keep going through those. Keep your postulates, keep your theorems memorized. If you've got a running list, go through that as well. Whatever you do, make sure you're keeping all of these informations in the front of your mind. Not to add to the list, but I'm adding to the list. These are the other properties of parallelograms. Okay, so we just proved this one, but you can actually prove all of these as well just as easily. Okay, now all of these are theorems, but they don't have a nice name to them. So in your proofs, you're going to be using these abbreviations. Okay. I'm going to let you pause the video and write these down right about now. I'm assuming you have. I'm just going to keep talking and I'll explain them. The first one is that opposite sides are congruent. The next one is that opposite angles are congruent. Okay. Then you have that supplementary or same side interior, or consecutive as they have it. Consecutive angles are supplementary as well. And the last one doesn't really have a picture because it's kind of hard to draw, but I'll try to do it anyway. You have a parallelogram. That's a bad one. That's better. All right, you have a parallelogram, and then they have diagonals. And the diagonals go from one vertex to the other. So those are my two diagonals. All right, and these bisect each other. That was easier than I thought. Okay. Now, something to be careful about on this one. That just because the diagonals bisect each other does not mean the diagonals are equal to each other. So bear that in mind. They bisect each other, but they are not necessarily equal to each other. Now that we've gone over all of that information, the video is going to pause and you're going to try to do these two problems on your own. Good luck. Okay, here is the answers and the work. Now on that first problem, I showed you both ways you could have approached it. You could have either have used that opposite angles are equal, or that same side interior angles are supplementary. Either one you wanted to use. On the second problem, that was really the only way to set it up and to do it. So hopefully you saw that. All right, let's move on. Another proof. I knew you'd be thrilled. Okay, what I want you to do is, given all that information, so we have the definition of parallelograms, and we have all of those theorems, all those properties we just went over, all of that's fair game right now. Go ahead, pause the video, see how far you can get, and then play the video and see how well your answer matches with mine. Go. I assume you're back, so let's get going. Now, we are given that both of these figures over here are parallelograms. Now, we just learned a lot of properties and a lot of things that go with parallelograms, so I'm going to read my proof, where I'm going, to see what information would be most helpful. All right, and I'm trying to prove that HL is congruent to, or HJ is congruent to ML. So those are segments, and as I look at my picture, I notice that HL and LM, where I'm trying to go, those are opposite sides of parallelograms. Okay, so I'm going to go with that and see if I can get somewhere with it. So due to the fact that opposite sides of parallelograms are congruent, I know that HJ is congruent to PK, and then, because this is a parallelogram, and then because PKLM is a parallelogram, I know that PK is congruent to LM. Okay, so PK is in the middle there. So eventually I'm probably going to have to do a transitive. Oops, that's not how you spell that word. A transitive property to connect them all. That's the logic. Let's get started. So here we go. I have parallelogram HJK and parallelogram PKLM. Then I have that HJ is congruent to PK, and that PK is congruent to ML. And again, this is because opposite sides of parallelograms are congruent. And then I know that HJ is congruent to ML because of transitive property. And that's what I'm trying to prove, so we can finish it out. How close did you get? Make sure if you didn't get what I got, go back and grade your proof. Okay? Did you use the same logic? Did you not? Did you do a different approach? Is that approach logically sound? Go back and test your proof. If you didn't try this on your own first, make sure you go back and try it again. Try to start it. Okay? All proofs are obvious once somebody else has done it. You got to make sure you can do these on your own. Now let's break from proofs and do a few more math problems. So with diagonals, remember the diagonals of a parallelogram are bisected. Okay, they bisect each other. So using that information, go ahead, try to solve these two problems. And here are the setups and the answers. Okay, remember, diagonals bisect each other, which means that those individual segments are congruent to each other. Okay? Also, as a reminder, A, B, X, Y, W, B, your variables can either be positive or negative numbers. Okay, variables are just placeholders. It doesn't matter technically what they are. What you cannot have is a negative side length. So it's all right in these problems if ever you get A is -3 or something. But make sure you plug that negative number back in and see if you have a negative side length, because then you have problems. Last but not least, coordinate geometry. Bringing on back the coordinate plane. Now with parallelograms, there's a lot of different information that can be proven algebraically. Okay, you can prove if two lines are the same length with the distance formula. You can prove if something is in the middle or being bisected, the midpoint formula. Okay, so all of those things can be proven. Let's do an example. Right now we have a parallelogram FGHJ. So I'm going to plot those points first and then read the question to figure out what I'm doing. So F is -2, 4. Label your points as well. G is 3, 5. You may have already figured this out, but I'll just remind you, if you don't plot your points correctly, you run into a lot of problems. All right, so there are my 4 points, and that's my parallelogram. And the question is asking me to determine the coordinates of the intersection of the diagonals. Okay, so I need the intersection of the diagonals. So I'm going to think about all my diagonal facts. And currently, the only diagonal fact I have is that the diagonals bisect each other. Bisect looks weird. It's probably not spelled right. Oh well. Okay, so diagonals bisect each other. Now thinking in terms of graphing, that means I need to find the midpoint of each diagonal. If I do that, I'll have the coordinate of their intersection. So currently, if I would have tried to just draw them and find the intersection with there, I have 2 big problems off the bat. Number 1, I'm not that good an artist, so my lines aren't exactly straight. Number 2, the diagonals might not intersect on a nice, neat point. However, if you draw your lines straight, you can at least get into the ballpark and you can check your algebra with your educated guess on your graph. Okay, so let's do this. I need to find the midpoint of point J and G. So J and G, and then F and R, H. I don't know where R came from. Now, if we do this right, both coordinates will be the exact same thing. As a reminder, our midpoint formula is x1 plus x2 over 2. And then we have y1 plus y2 all over 2. So I'm going to have -3 plus 3 over 2. And then -4 plus 5 over 2. I actually got pretty close. Not bad for not straight lines. All right, and now I'm going to do FH. So, small point. Whenever you have 0 over something, don't get freaked out. Anything divided by 0 is 0. The only problem happens is whenever you have 0 in your denominator, because that just doesn't mathematically work. All right, so now we're going to do the next one. So -2 plus and you can see where this is going, but I'll finish it out anyway. And yay, they are the exact same. So this is the coordinate of the intersection of the diagonals. And I actually wasn't too far off in my educated guess over there. So there's going to be a lot of different problems like this. I may ask you to find the length of the diagonal. You might be asked to find the length of one segment of the diagonal. Okay, so make sure you remember the distance formula and your midpoint formulas, because those will come in handy pretty soon. All right, and that is it for this video. If you have any questions, make sure you write them down, and I will see you on Monday. Bye.